All right, welcome to The Explainer. Today we're going to try and untangle one of the strangest, most, frankly, mind-bending ideas in all of science, quantum entanglement.
You're looking at the words of Albert Einstein himself. Spooky action at a distance. That's what he called it. He found this whole concept so deeply weird, so against all common sense, that it made him question the very fabric of reality.
So, what is this spooky connection? And could Einstein, one of the greatest minds in history, have actually been wrong about how the universe works? Well, over the next few minutes, we're going to dive deep into that mystery and find out how a huge scientific debate finally gave us the answer.
Okay, let's really get into it. To understand why entanglement is so, well, spooky, we first have to see why it's nothing like the world we experience every single day.
Okay, so people love this analogy of two gloves. Imagine you put a left and a right glove into two separate boxes. You keep one and you mail the other one to, say, the other side of the planet. The moment you open your box and see a left glove, you instantly know the other one is a right glove, right? No magic there. But here's the catch, the part that makes quantum mechanics so wild. With the gloves, it was always a left glove in your box. The outcome was set from the beginning. Entangled particles? They don't have a set state. They are in a kind of limbo until the very instant you measure one. And that limbo state has a name. Superposition. It's this wild idea that a particle can be in multiple states all at the same time. You know, like a spinning coin before it lands. It's not heads, it's not tails, it's kind of both. And that is the secret ingredient that makes the spooky connection of entanglement possible.
You can imagine this idea didn't sit well with everyone. In fact, it sparked one of the biggest showdowns in 20th century science. We're talking about a battle of ideas that basically put the universe itself on trial.
So in one corner, you have Albert Einstein. He was all about local realism. Basically, common sense, right? He believed things have real properties even when we're not looking, and that nothing, no signal, no information can travel faster than light. So for him, entanglement had to mean there was some hidden information we just couldn't see yet. But in the other corner, you had Niels Bohr. He was like, nope. He argued reality is fundamentally fuzzy, it's all probabilities. And asking what a particle was before you measured it, to him, that question just didn't make any sense.
And can you believe it? For almost 30 years, that was it. Just a big philosophical argument. It was a heavyweight debate about the nature of reality with absolutely no way to prove who was right. It was just talk.
But then the 1960s happened, and a brilliant physicist came along who figured out how to stop talking and start testing. He found a way to actually put reality on the stand. And that physicist's name was John Bell. What he did in 1964 was, honestly, a complete game changer. He published this theorem that took that philosophical deadlock between Einstein and Bohr and turned it into something you could actually test in a lab, a real scientific question.
So he came up with this mathematical rule, which we now call Bell's inequality. You can think of it like this. It's a line in the sand. If Einstein was right about that hidden information, then the results of any experiment you run would have to stay below that line. But if quantum mechanics was the true story, the results would blow right past it. They'd violate the inequality.
So there it was, a clear test. All scientists had to do was go into the lab and ask nature herself, which one is it? Are you the common sense universe of Einstein, or are you the weird, spooky universe of quantum mechanics?
Now, the answer didn't come from one single dramatic experiment. It was more like a slow burn detective story, playing out over decades with more and more precise tests. You can see the whole story laid out here. It really kicks off in 1972 with John Clauser's first experiments. Then, a decade later, Alana Speck comes along and closes some major loopholes people were worried about. And this just kept going, getting more and more precise, until 2015, when scientists ran what they call loophole-free tests. At that point, the evidence was just undeniable.
And the final chapter? Well, that was written in 2022. The Nobel Prize in Physics went to Aspect, Clauser, and Zellinger for all this groundbreaking work. The verdict was in. The universe had spoken. And it's spooky. Quantum mechanics was right all along. Einstein, for all his genius, was wrong about this one.
So, okay, Einstein was wrong. But why does this matter to us today? Well, because this isn't just some dusty old debate. That spooky phenomenon is now the engine driving a technological revolution that's happening right now. Entanglement is literally the key ingredient for a whole suite of new technologies. We're talking unhackable communications through quantum cryptography, quantum computers with revolutionary processing power, even a future quantum internet. It's the whole shebang.
And one of the most mind-bending applications, quantum teleportation. Now hold on, this isn't Star Trek. We're not beaming people around. What it does do is use entanglement to transfer the perfect, complete quantum information, the very essence of a particle, from one place to another instantly.
And when it comes to computers, entanglement is the secret sauce. See, a normal computer gets more powerful one step at a time, in a straight line. But when you entangle quantum bits, we call them qubits, their power explodes exponentially. To put that in perspective, a quantum computer with just a few hundred entangled qubits could tackle problems that are impossible for even the biggest supercomputers on Earth today.
And believe me, this isn't science fiction anymore. Very recently, in 2024, scientists were able to teleport quantum information through live, busy fiber optic internet cables. And up in space, China's Messias satellite is already using entanglement. This future is literally being built as we speak.
So what's the big takeaway from all this? Einstein's spooky action, this thing that bothered him so much, has gone from being a weird paradox to being a real-world tool. Do we fully understand why it works the way it does? Not really. But just like electricity a century ago, we don't need to fully understand it to harness its power. It's becoming this fundamental commodity that's going to power the next generation of technology. The spooky mystery is now our spooky reality.